What if machines could think? This question, once the realm of science fiction, became a driving force for a generation of brilliant minds. From the intricate gears of Babbage's analytical engine to the elegant logic of Turing's machine, the foundations of artificial intelligence were laid brick by brick, paving the way for the intelligent machines that are rapidly transforming our world. The Industrial Revolution wasn't just about steam engines and factories. It also reshaped how people thought about machines and logic. In this fertile era, Charles Babbage imagined a future where calculations were no longer slow and error-prone. His analytical engine wasn't just a calculator. It was programmable, capable of storing data, following sequences of instructions, and performing any kind of calculation. These ideas, structured computation and data processing, still form the backbone of artificial intelligence today. Babbage had the vision, but Ada Lovelace saw the machine's true potential. She recognized that the analytical engine could go beyond numbers. It could manipulate symbols and execute complex instructions. She wrote what is now considered the first ever algorithm designed for a machine, proving that machines could follow logic in ways we'd later call programming. Lovelace understood that machines wouldn't replace human creativity but extend it. But her insights sparked a deeper question. If machines could follow logical instructions, were there limits to what they could compute? In 1931, Kurt Gödel delivered a shocking revelation. Some truths will always lie beyond the reach of any logical system. This wasn't just a mathematical curiosity. It raised deep questions about the limits of knowledge itself. As mathematicians wrestled with these questions, a young Alan Turing became fascinated by the nature of computation itself. Alan Turing wanted to define the very essence of computation. What does it mean for something to be computable? This seemingly simple concept was profound. It became the foundation of all modern computers. Turing realized that a universal version of this machine could simulate any other machine just by changing its instructions. This was a breakthrough. Turing had mathematically described how all computation works, but Turing's work didn't stop there. Are there problems that no machine can ever solve? The answer to Turing's question? No. This became known as the halting problem, proving that some problems no computer, no matter how advanced, can ever solve. This set a fundamental limit on computation itself. During World War II, he built machines that cracked the German Enigma cipher. His work shortened the war and saved millions of lives. He is celebrated as the father of modern computing, and his ideas continue to shape AI and machine learning. As Turing explored what machines could compute, another pioneer, Claude Shannon, was laying the groundwork for how machines could communicate. Claude Shannon, working at Bell Labs, had a brilliant insight. The elegant simplicity of Boolean algebra. True, false, on, off, 1 or 0. He realized that Boolean algebra could describe the behavior of electrical circuits. The zeros and ones he defined became the lifeblood of digital world and ultimately artificial intelligence. But while Shannon gave us the language of computation, how could machines actually learn? Warren McCulloch and Walter Pitts discovered that when neurons were connected in networks, they could perform computations. This was a radical shift. Instead of programming intelligence step by step, intelligence could arise from many simple units working together.
Think of a thermostat. It constantly monitors the room temperature and turns heating or cooling on and off to maintain the desired setting. Now apply that idea to intelligence. Just as your body adjusts to maintain balance while walking, machines could use feedback to refine their actions, learning from experience. Wiener's work showed that intelligence isn't just about processing information, it's about adapting. Cybernetics provided a framework for understanding intelligent behavior. Influencing early AI research, this was a crucial leap forward, moving beyond machines that simply compute to machines that could learn and self-regulate. While Norbert Wiener explored how machines could regulate themselves, John von Neumann was revolutionizing the very architecture of computers. They were now programmable. One of the biggest hurdles was how to store both the data and the instructions for processing that data. John von Neumann solved this problem with his revolutionary stored program architecture. By introducing stored programs, computers were no longer locked into a single function. They could be reprogrammed dynamically to tackle new tasks. This flexibility was crucial for AI. But AI needs more than processing power. It needs to learn. Scientists looked for inspiration, not in machines, but in the human brain. Donald Hebb, a Canadian psychologist, wanted to uncover the biological mechanics of learning, how experiences physically change the brain, memories form, and intelligence develops. His most famous insight? Neurons that fire together wire together. He also proved how entire neural circuits store complex patterns of information rather than just single bits of knowledge. The idea that connections strengthen with repeated use became a core mechanism in machine learning, allowing artificial neural networks to adjust their weights over time, learn from data, and refine their performance. The idea of cell assemblies influenced how AI systems organize and retrieve information, forming the foundation of deep learning architectures today. Researchers could now explore how machines adapt just like the brain. Understanding how learning works was a crucial breakthrough, but theory alone wasn't enough. Scientists needed machines powerful enough to put these ideas into practice. A team of engineers in Australia built CIRAC, one of the world's earliest stored program computers. True progress came from the partnership between human expertise and machine capabilities. At NASA, two remarkable women demonstrated the power of human computing collaboration. Dorothy Vaughan, a brilliant mathematician and computer scientist, led the West Area Computing Unit at NASA, ensuring her team was trained in programming. Her leadership and foresight were instrumental in integrating computing power into NASA's research, paving the way for future advancements in space exploration. Katherine Johnson, another trailblazing mathematician, was one of NASA's hidden figures. Her precise calculations were essential for the success of some of NASA's most historical missions. She embodied the power of human-computer collaboration. They were pioneers in STEM, breaking barriers for women of color, demonstrating the importance of diversity in driving innovation. Could machines do more than just calculate? Could they think, learn, and reason like humans? A small group of scientists believed they could. Claude Shannon built a mechanical mouse that could navigate a maze using trial and error, an early form of reinforcement learning, the foundation of self-driving cars, robotics, and gameplay. At IBM, Nathaniel Rochester developed some of the first AI programs using heuristic problem solving to mimic human reasoning. Nathaniel's work laid the foundation for symbolic AI. Lisp, List Processing Language, invented in 1958. While McCarthy focused on symbolic AI, Marvin Minsky had a different question. What if machines could learn like the human brain? Minsky built SNARC, Stochastic Neural Analog Reinforcement Computer, the first artificial neural network. Meanwhile, at the Rand Corporation, Alan Newell and Herbert Simon created Logic Theorist, the first AI program that mimicked human reasoning. By the late 1950s, AI had three competing approaches: symbolic AI, neural networks, and hybrid models. AI was no longer just a theory, it was becoming real.